The heating of a cool body by a warmer body is an important form of energy transfer between two systems. And the amount of heat transferred between two bodies can be quantified by the heat transfer equation, where the heat transferred is equal to the mass of the body by the specific heat capacity by the change in temperature of the body. And this can be written in terms of the number of moles and the molar heat capacity also, where the specific heat capacity is the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius or Kelvin. Because a change in temperature in degrees Celsius or Kelvin should yield the same amount of heat transfer. And similarly, the molar heat capacity can be written as follows. Now, for example, if we drop a hot iron block with the following mass, initial temperature, and specific heat capacity, into a styrofoam cup holding water with the following properties. Then the heat flows from the hotter body, being the iron block, to the water. And that causes an increase in the temperature on the thermometer. And the amount of heat transferred to the water can be quantified using the heat transfer equation. And here we have the final temperature minus the initial temperature of the water. And similarly, the heat lost by the iron block can be calculated as follows. And assuming there's no heat lost to the environment, when thermal equilibrium is reached, we have the following condition. And you can use this to solve for the final temperature, where this should be closer to the temperature of the water, which has a higher specific heat capacity, meaning it's harder to change its temperature, and also having a higher mass is going to result in the final temperature being closer to that of water, which I'll leave for you as an exercise. The first law of thermodynamics is a statement of conservation of energy, where the change in internal energy of a system is equal to the heat flowing in or out of the system, plus the work done on or by the system. So a typical model used in thermodynamics is an ideal gas, and this constitutes our system that we're analyzing, and everything else in the universe is the surroundings. And here we have a piston that can move up and down to do work on the system, and the heat reservoir enables heat to flow in or out of the system. So heating a system increases its energy given that the temperature increases, and that causes the piston to move upwards by some amount, and the pressure exerted by the forces acting on this area of the gas volume gives the average force, and multiplied by delta Y gives the work done. So if the piston moves upwards, the system does work on the surroundings. So therefore this can be written as pressure by the change in volume. And therefore our change in internal energy can be written as follows. So if the change in volume is positive, then the system loses energy. So a positive change in volume yields a reduction in internal energy. So here we covered the basics to use in this chemistry unit. Recall the first law of thermodynamics, which says that the change in internal energy of the system we're analyzing is equal to the heat going in or out of the system and the work done on or by the system. So if the change in volume is positive, then the system expands and the internal energy decreases. And the internal energy is a state variable because it only depends on the initial and final state of the system, not on the process that brought the system from the initial to the final state. Whereas the heat and work are not state variables because they depend on the process. Now a state variable that we'll use in chemistry is enthalpy, which is defined as the internal energy plus the pressure by the volume of the system. And therefore the change in enthalpy can be written as the change in internal energy plus the pressure by the change in volume plus the change in pressure multiplied by the volume. And if we substitute for the internal energy, then these cancel, and for a system under a constant pressure, then the change in pressure is 0, and therefore the change in enthalpy is equal to the heat energy absorbed or released at constant pressure. And most chemical reactions occur under this condition, so we use the change in enthalpy rather than a change in internal energy. Calorimetry experiments are used to measure the transfer of heat, and under this configuration we have a styrofoam cup or a coffee cup, which is a good insulating material, a thermometer, a stirrer to mix reactants, and a loose fitting lid which exposes the reactants or bodies to a constant atmospheric pressure. Now for example, if we dissolve sodium chloride, which is a solid, in an aqueous solution, it dissociates into ions. So before the sodium chloride dissolves in water, we have an initial temperature reading, and after it dissolves, we have sodium and chlorine ions in the solution, and the dissolution process causes an increase in temperature. And the heat absorbed by the solution at constant pressure is equal to the mass of the solid plus the mass of the water, which now form the solution, multiplied by the specific heat of the solution, and multiplied by the change in temperature. And therefore the heat released due to the dissolution of the ions at constant pressure is a negative of the heat absorbed by the solution. So therefore the dissolution process is exothermic, because the temperature of the solution increased. Sodium chloride is dissolved in water. In a styrofoam cup, calculate the heat released due to the dissolution process if an increase in temperature is recorded, and a specific heat of the solution is given. Well, the heat absorbed by the solution at constant pressure is equal to the mass of the solid plus the mass of water, which is the same as 100 grams, multiplied by the specific heat of the solution, and multiplied by the change in temperature. So the heat released due to the dissolution process is the negative of the heat absorbed by the solution, where we use 3 significant figures. And at constant pressure, this is the same as the change in enthalpy.